pronounce your
It's
name.
okay. It's fine.
Okay.
It's good.
She's from Institute of Mathematics from the University of Silesia in
Katowice.
I'm sorry. You're welcome. Her topic is on the screen.
Thank you very much for the introduction. So I hope that you can hear me.
Yes, we hear you. Everything is fine.
Good. I have problem with my throat today, but I hope that I will be able to talk for the 25 minutes. So I am going to talk about these substochastic semigroups for initial boundary value problems. So meaning that we are working in L1 spaces. We have the state space here, which is defined with the set E with some sigma finite measure on it, as well as a space denoting the boundary space, let's say, so that it will be denoted here with this partial, this additional notation E subscript partial, so that we have two L1 spaces really. And so the one will be connected with a boundary condition, and that will be connected with our initial conditions, right? So we have additionally the setting, the general setting here is that we have really a subspace of this L1 space. It has to be a linear subspace. And we have, let's say, four operators, right? So we have two operators acting on this space, on this subspace D, with values in our L1 space, and two operators psi, psi0, psi0, and psi with values in this boundary L1 space. So that the general boundary value problem can be described like that, right? So we have this U prime of t is the sum of these two operators A plus B over this acting on U of t, and here is this boundary condition, meaning that we have this psi 0 of U of t is the psi of U of t, and the initial condition we start with f from the L1 space. And the problem, so the initial, what we know additionally is that this operator A restricted to the kernel of psi 0 is actually the generator of a positive semigroup. So that here, I mean, in fact, we don't really need this dense assumption here, because it will follow from this assumption, like restriction of this operator A to this kernel is the generator. And for us, what we want to, let's say, we want to have something like easily verifiable condition given on these four operators, so that we can actually say that this there is a C0 semigroup given giving the solutions of this problem, right? So let's start first with the problem when here this operator B does not exist. I mean, we take B equal to 0. And so we have this operator A restricted to this kernel of, I mean, to the domain of this operator A psi, so that this boundary condition holds here. So that would be, in fact, a restriction to the kernel of the difference between psi0 and psi. So, so first the question is, okay, so when actually is this operator psi the generator, right? So of course, first we can ask, okay, do we know when this is the generator of a C0 semigroup? But maybe we have something general idea when it is the generator of a positive semigroup. But what is really interesting for us, whether it's actually when it is the generator of a substochastic semigroup. So recall that a substochastic semigroup here is just a positive semigroup of contractions, right? And a stochastic semigroup is the most interesting for applications because here we have the conservation of the densities. So so in this situation, it's just the conservation of the norm, right, in the L1 space. So let's, so of course, we don't, I mean, the most general result when we know that this operator generates a C0 semigroup is is Greiners Theorem. But it has the I mean, it has additional assumption. I will recall soon what they are, but it's relative. It is only it can be applied only when psi is bounded. And of course, there are some specific results. But I will start with this Greiners Theorem. So recall it. So we know that it is actually the generator of a C0 semigroup if the following holds. So to simplify the presentation, so here condition A says that both these operators A and psi0 are closed and psi0 is on 2. Additionally, the operator B has to satisfy these so-called Greiners conditions, meaning that here it has to be the norm of psi0 of f has to be bounded from below by some lambda times some constant times the norm of f on the kernel of this operator lambda minus a. And of course, C is this assumption that A naught being the restriction of A to the kernel of psi0 actually generates a C0 semigroup, and that psi is bounded. So these four assumptions imply that a psi is actually the generator of a C0 semigroup. So let's look more closely at this condition. So in particular, this condition A implies that we can write this domain of these two operators as a direct sum of these two subspaces. And additionally, when we restrict the operator psi0 to this kernel, we get an operator which is invertible. And then so that what and the so-called Dirichlet operator here will be denoted by psi of lambda, being the inverse of this operator, is actually bounded, right? So this is called this is so-called Dirichlet operator due to the fact that it satisfies this kind of a general Dirichlet boundary condition. Okay, so because of this invertibility. Right. So here that has to be invertible for I mean it's that it is invertible and bounded is the consequence of this assumption A. It was found by Greiner, and then this condition B, which was further imposed, implies actually that this operator, this Dirichlet operator, has norm bounded by this 1 over lambda psi. So, so that's the consequence. And additionally, if we know that psi is bounded, then we can bound the norm of the composition of psi of this Dirichlet operator with this operator psi, and it is bounded. And then this allows us to conclude that if we take the I mean, for lambda sufficiently big, this is actually smaller than 1. So identity on the state space minus this composition is actually an invertible operator, and it is used to define the resolvent of the operator A psi. And that if we have this resolvent, then one can then, so the proof then follows that the standard theorem can be used to get the C0 semigroup. So, so what we actually here have is that the psi is defined on L1 and psi lambda, then the composition is here well defined. But if we have unbounded psi, this formula does no longer holds, right? So what we were looking at now, then let's say that so suppose that we are in this situation that we have positive psi 0, and then of course additionally we will have as well positive psi. But what are the consequences of this assumption is first that this Dirichlet operator will be positive as well. And then additionally, we want to have this kind of a verifiable condition. So what we usually do in for substochastic semigroup, if let's say A would have been a generator of a substochastic semigroup, then this integral has to be smaller than 0, right? So, what we actually look at, we impose this condition that we took together these two integrals, so the difference of the two. And of course, in this situation, if we know that this operator is positive, then we can actually conclude from this inequality that this norm of these Dirichlet operators are smaller than 1 over lambda, and we automatically have then this Greiners condition being true. So in fact, for psi, let's say bounded, which now has to be really positive because psi 0 is positive, then of course we have this, let's say, a C0 semigroup. But as I said, we wanted to go into unbounded psi, and what we did, we actually had this theorem with Piotr Gwiszcz, and we actually started with the following assumption that we have A and psi 0 are such that only what is required here is that this Dirichlet operator really exist, right? So we assume that psi0 restricted to this kernel has a positive right inverse. So that's the assumption. We don't assume any closedness and nothing like that. And then, of course, the second assumption is that A naught is a generator of positive semigroup, and then we take this positive psi, and now instead of so we compose psi of lambda. Psi of lambda is defined on the whole L1 on the boundary space, and has values in the domain D, and then we can compose it with psi, and of course now we look at this operator, and so it makes sense, and then actually this operator is invertible, and with positive inverse for all lambda sufficiently large. And this condition, which we had on the previous slide. Then these four assumptions actually imply that this operator A restricted to the kernel of this psi0 minus psi just generates a positive C0 semigroup. So we can look at this proof, a simple consequence. This is, let's say, consider the product of both spaces. And on this product, we define the norm, right? And we define the two operators on this product space. And what we have, these operators, we have take the operator A here with these values. So we have psi0 here in the boundary space, and we have operator B, which acts only on the boundary space. And this operator actually has a domain, which is the closure of this domain is this L1 space and 0 on the other variable. And here what is important is that actually B composed with this resolvent of operator A actually has a spectral radius smaller than 1, so we can invert identity minus this operator, and we have the formula for the resolvent of the sum of these two operators, and that's then we look at the part of this operator in this space, and this part of this operator actually is the generator of our positive semigroup. So, here the resolvent is of the formula like that. So we have now this composition. Here is the resolvent of operator A0, and here we have a bunch of other operators, which when psi is actually bounded, it reduces to the same as it was in Greiners theorem. So that's the idea of the proof, and let me start with a simple example here. How it works. Let's look at this McKendrick population model. So that's the classic example, and here we have the death rate, the birth rate, and A is the age of a population. And the operator A is here this differential operator, and as boundary operator, we have this value at 0, and on the other hand, we have this. So now all what is needed here is that mu and beta are positive, I mean non-negative, right? And we can easily invert this psi zero, so that's the Dirichlet operator. And we can easily check that this norm of psi composed with psi of lambda is actually, I mean, it is less than 1 for all lambda bigger than so-called intrinsic growth rate for this McKendrick population model, if it exists, right? If it does not exist, then it does not, I mean, does not apply. But in particular here, when, let's say, when beta would have been equal to mu, then that is always true. And of course, it is as well true when we look at this McKendrick population model in the case of cell populations, when beta is twice the birth rate and mu is the death rate plus birth rate. So that's how it looks like. So we automatically have the that this operator A here a psi is the generator of a positive semigroup. So so we want to have now something easily verifiable for having a substochastic semigroup. So what we do? So assumption first and second are like before, but now psi, we only assume that it is actually positive. And then we add here additionally, we add one more integral here. So we take here the integral over this difference of these boundary operators. So of course, when we are in the kernel of this operator, then this integral disappears, right? So if this holds, we can here have either equality or inequality. And I use, of course, we could have used only that, but if it is, we have a characterization like the operator A psi is the generator of a stochastic semigroup if there is equality, even only if this condition holds, or a substochastic semigroup in this more general condition is true. Right. So here, of course, if this norm of this operator is less than 1, then automatically this condition is satisfied. So let's see for an example how it can be applied in a, let's say, a simple gene expression model. So all proteins are made by being I mean, from DNA, through transcription, there is produced mRNA, and then mRNA gives the recipe how to make a protein. So it translates all these genes on for the production of protein. And what was observed experimentally is that actually these both the transcription of the DNA into mRNA or the translation, all right, are done in a discontinuous fashion in such a so-called, here you can see that from time to time something was produced, and here is another picture showing that showing that actually what happens is that the molecules are degraded, and then there is this production of these molecules, and then again they are degraded, and so on. So so a simple model for that is that we can look at this gene product being produced at some random times and in some random amounts, so-called bursts. And if we take as the amount of molecules being a continuous variable, then the degradation can be described by this simple differential equation. And what we assume here is that the bursts and these times between consecutive bursts are actually are independent and have the same distributions with given densities h and h of t. And in this fashion, we get this h-structured equation. Here, A is just the time from the last burst. And so we have this now additional term here denoting the degradation of the proteins, and here the initial the boundary condition is that here showing the production of the protein. And rho is just the rate of occurrence of these bursts, and in that situation, the operator psi of lambda is again easily verifiable. And its norm is strictly less than 1 for all lambda positive, because it's the Laplace transform of this the time of the first, I mean of the time of the length of the time between consecutive consecutive bursts. And in this situation, because here if we integrate all these, so the operator A will be minus that, and minus that, and if we take this, all this substitute to this theorem, then we see that it actually we have a stochastic semigroup. So we have that this operator generates a stochastic semigroup. And this is a simple example of a large class of so-called piecewise deterministic Markov processes. So what are they? So in this, so to show you just for this particular example is that we have here actually two variables, x and this a, right? So they x of t and a of t satisfy these two equations. So we have differential equation in the state space, and this is just between this occurrence of these so-called here bursts, we call them jumps, right? And then what happens at time tn, so thus we have to, in this particular situation, we take the value of this random of this x, and we add this random variable at n here, and we so that's the production, and we reset the time to 0. And in this situation, we have actually this Markov process can be characterized with three characteristics, which is a flow, being the solution of this differential equation, intensity, meaning the intensity of these jumps, and then we have this jump distribution here in this particular example is just this distribution, what happens when we go from a given point to a given set. So that's the probability of transition from the point to the given set. In this example is this integral showing the distribution of this random variable. So for that situation, if we have a stochastic semigroup, so of course this the question is whether this stochastic semigroup is the stochastic semigroup, meaning that it actually describes the distribution of this process, right? Of this. So if we start from an initial random variable which has a density f, then we want to know that actually our stochastic semigroup gives this density of x at time t. So, and that's the case. And we actually did a large paper on that, characterizing these processes and their stochastic semigroups. That was in another paper. And its summary is in my last paper on this subject from 2020. And let's say here the initial boundary value problem. So we can add here this operator B. We have everything like before. We add a positive operator, and we add under this integral operator B. And here we have additionally this one part, and the rest stays the same. And we have this characterization that actually now A plus B generates this substochastic or stochastic semigroup, even only if now the range of this matrix operator contains this space L1 times 0. And but what is more important, maybe for application and this this piecewise deterministic Markov processes, is the fact that we actually have an extension here of, we have an extension of Kato theorem showing that actually always from 1 to 4. This 4 condition implies that there always exists a substochastic semigroup which has a generator being an extension of this operator. And this existing substochastic semigroup is actually the one which corresponds to our piecewise deterministic Markov processes, which are described with these 3 characteristics, but we turn the 3 characteristics into operators, and these operators are the following. The operator A is described as a operator which corresponds to the flow, and here is the intensity. And then, of course, we have to somehow here trace the function on the boundary. And then everything was here identified. This operator psi0 is the trace on the incoming boundary, and psi corresponds to jumps to the boundary, and B to jumps to the state space.
Marta, unfortunately, we don't have any time. Just 1 minute before the next.
Yeah, that's all.
I'm sorry for interrupting you. Just
yeah.